for inviting me to this virtual math fest to give a talk, and many thanks to them for organizing such a nice math fest, because it was when it was announced, it was sort of it was, I think, the kind of first in India, but then IISER also happened just before it. But in these difficult times, to organizing this is in such a big scale, it's a really awesome activity. I mean, it's really big effort, and I really would like to thank the organizers, the postdocs who organized it. Big thanks to them. Okay, so I will talk about this non-local scalar field equation, and it's basically an expository article, and I have tried to keep it like elementary, keeping also in mind of for the students and the people from analysis who are not from exactly this field. Okay, so let me see. Okay, so I will just a second. Okay, so I will talk about this scalar field equation, which I denoted as E. So this is this reads as minus delta S U plus VXU equal to GXU in Rn. So I will describe each of these terms. What is this? What these terms means. So just first, Vx is a potential and Gxu is a nonlinearity. I will again talk about more that what kind of nonlinearity we are dealing with here, and what is this operator here? The operator what I have written as delta SU. So to define the operator, this delta SU, I need to first, I will define it on the Schwartz space function. So, and what is the Schwartz space function? So these are the rapidly decreasing C infinity functions. So by that, what I mean that suppose I say that phi is in the Schwartz space is, that means that phi is C infinity. And if you take any order derivative of phi and multiply with any order polynomial, then the product of that function, I mean, it has the property that it goes to zero at infinity. So that means it's rapidly decreasing at infinity. So it actually, there is a topology in this space which is generated by this seminum. This is a standard Schwartz space called. Okay, so on this Schwartz space, this operator, this minus delta is defined. Yeah, it is defined in this way. So it is defined with this integration. So it's called integral differential operator, and it is defined in the principal value sense, because you see there is a singularity at x around x. So what you need to do is that you have to take a small ball around x, and you have to remove that small ball and then take the limit. So that's how this operator is defined. And this is called a non-local operator. And why that is clear then why it is non-local, because you see this to know the value of this minus delta SU at any point x, you need to know the value of u in the entire space Rn. So it's not just you need to know the value, like when it is s equal to 1, when it is just a Laplacian, you know that to know the value of Laplacian of u at some point, you just need to know locally u at that point. But it's not the case here. So that's why it is called non-local operator, and CNS is a constant which is given by this. Now this minus delta S actually is called the fractional Laplacian, and I will just tell in a minute that why do we actually call it as the fractional Laplacian? I mean, what's the motivation for it? Okay. So next, using this so here there is a constant. Okay, now if you see if you study the asymptotics of this constant, then one can actually see that s goes to 1, this minus delta S u is actually approaching to minus Laplacian, and as s goes to 0, this is actually approaching to u. I mean, so you can see that there's a limit, it's actually going to as s goes to 1 is that Laplacian. And also there is another motivation behind it, calling the fractional Laplacian, which is the main motivation. So you can see that when s is in 0, 1, we can actually equivalently define fractional Laplacian or minus delta S operator. And this actually generalizes the definition of from minus Laplacian to minus fractional Laplacian. So you see this one, like when s equal to 1, this is very well known, because if you take the Fourier transformation of Laplacian, so this is inverse of the Fourier transform, so you can take it on this side. So what you can see that if you take the Fourier transform of the Laplacian, you know that what it is. So it is nothing but xi square u hat, the xi square Fourier transform of u. So that means you can define minus Laplacian u by taking the Fourier inverse of this one when s equal to 1. So question is that can we generalize it? Yes, we can. So what we have written here, the previous definition, it can be shown that using some change of variable and Fourier transformation, that when s is in 0 and there is an equivalent definition, we can actually define it in this way. Okay, so you can to know about more about this fractional Laplace, and that's why it's called the fractional Laplacian. So to know more about this fractional Laplacian, we can just you can just see this Hitchhiker's Guide, which is very, very well written and for the beginners actually. Okay, so now where does this fractional Laplacian appear? I mean, this appears in many, many different contexts. For example, like thin obstacle problem, optimization, finance, phase transition, crystal dislocation, soft thin films, film propagation, etc., etc., minimal surfaces, etc. And also, fractional Laplacian provides a simple model to describe certain jump-Levy process in probability theory. Now, that's the first natural question one may ask, that what is the difference between Laplacian and fractional Laplacian? I mean, okay, it's a generalization. Are there, when we deal with the equation with fractional Laplacian, what could be the differences? What are the difficulties? Why it is different? Is it just a generalization, or there are really differences? So there are actually plenty of differences, many differences. I here just like to point out few of them. So first of all, as you first noticed itself, that when you want to define classical Laplacian, you do integrability properties of u, right? But when you want to define this fractional Laplacian, to define this, to make it well defined, one needs this integrability condition on u. Second, another condition, what I can say is that, so suppose you know that Laplacian at some point is non-zero. So for example, you suppose Laplacian u0 is 1. Okay. Now, if v is close to u in C2 norm, then you can always say that Laplacian of v at that point is also non-zero. Okay. But this is not at all going to be true in when you go to the fractional Laplacian. In fact, what we can show is that when you take given any epsilon greater than 0 and bounded smooth function u, you can always find a v epsilon which is close to u, that in C2 norm, that v epsilon minus u is less than epsilon in C2 norm, but it is harmonic in B1. So this is a very, I mean, there's a striking difference with a Laplacian case. So actually in the fractional Laplacian case, what happens that almost, I mean, every function is actually locally S harmonic up to a small error. Di Piero Savin Valdinoci in 2017. So next, another we all know that suppose u is a harmonic function in B1 and u is non-negative in B1, then you know that in supremum of u in a small ball, you can actually control by the infimum in that one. Okay, but when you go to the S harmonic function, I mean S harmonic function, you need not just u greater than 0 in B1, rather you need u to be positive, I mean non-negative in the intraspace Rn. You can see the proof here in Abatangelo Valdinoci, this one. And what are the other differences? There are many, as I said, I'm just pointing out only few. So one of the another striking difference is the growth from the boundary. So roughly speaking, if you consider solutions of Laplace equation, that has Lipschitz growth, linear growth from the boundary. Whereas if you consider the solution of fractional Laplace equation, it has only Helder growth from the boundary. For example, suppose I take U, consider U, which is continuous up to the boundary B1. And it satisfies this minus Laplacian equal to f in B1, and which is 0 on the boundary. Then one can actually show that U has this growth condition, Ux is less than equal to some, it can be controlled by 1 minus mod x. Okay, but when you go to the fractional case, I mean that S harmonic function, it changes. So you see, if you consider this simple function, x goes to xn positive, that's the to the power s. Okay, so it is S harmonic in the upper half space, but this is just a Helder continuous function with this Helder exponent S near origin. Now, another one is the global regularity in the differences. So if you consider the solution of this Laplace equation, they are smooth up to the boundary. But if you go to this fractional Laplace case, you can maximum expect the Helder continuity up to the boundary. So if you just go back to the where did I go? If you just go back to this equation one, this equation U, so there you can see that you can control the sup norm of gradient by this one. But in the case of fractional Laplacian, so you see this example, Ux equal to 1 minus mod x squared to the power s positive. So this is the positive part of the function. So this satisfies fractional Laplace equal to constant, but this is Helder continuous in B1. You cannot get more than that. And then another obvious difference which must have observed that Laplacian U, if you consider at 0 or any point or nothing about 0, so you need to know the value of U only at the coordinate axis, right? The coordinate direction. But for the fractional Laplacian, you know that it's not true. You need actually in the entire space Rn. So there are many. Anyway, I just wanted to show you just some of the few differences. Now, if I want to define what is the I go back to the original equation which I wrote first, the scalar field equation, because I will mainly talk about this equation E. So now question is that what do I mean by the solution of this equation? I will say something about weak solution, but to define the solution, I need to define something called fractional Sobolev space. So yeah, so I will define something called fractional Sobolev space. So s greater than equal to 0. For any s non-negative, I define fractional Sobolev space Hs Rn by taking all those L2 function for its j to the power s Fourier transform U. This is in L2 Rn. Okay, and this can be equivalently defined by completion of C0 infinity with respect to this norm. Since C0 infinity is that C infinity function with compact support. That is my notation C0 infinity. Since C0 infinity functions are in the Schwartz space and C0 infinity dense in HSRN, so using density argument, one can actually show that this definition, which I first wrote for the fractional Laplacian on the Schwartz space function, I wrote this definition. So it can be shown that this definition holds for any U in HSRN2. So we can extend it into the fractional Sobolev space. Okay, so now when S is in 0, 1, so actually one can show that this norm, this one is actually equivalent to this Gagliardo norm. So equivalently one can just, this is true for S in 0, 1, I repeat, for S greater than equal to 1, this is no longer true, this equivalence is no longer true. There is a counter example, and in fact this is finite only when S less than 1. So equivalently, one can define write HSRN norm of HSRN as L2 plus this Gagliardo norm. Okay, and HSRN is a Hilbert space for S in 0, 1, and you can write this. I mean, it is a Hilbert space anyway. If it is S greater than equal to 1, also it is Hilbert space. But when S is in 0, 1, you can write this inner product in HS as this L2 inner product, but plus this one because it's coming from this Gagliardo norm. Okay, now we also have a Sobolev, we also have the Sobolev inequality in HSRN. So he says that, so you take any U in HSRN, you can control the L2 star norms, 2 star equal to 2n by n minus 2s. You can control the L2 star norm by this Sobolev, fractional Sobolev norm, okay? And this is the universal constant. This depends on n and s. Capital S depends on n and small s. So there is a very natural so then therefore you can actually define now homogeneous fractional Sobolev space, which is denoted by HS dot Rn. So you take all those L2 star Rn. So now I'm not taking L2 part. I'm taking all those L2 star for which this is finite. And I have the corresponding norm. And again using density, you can actually show that Sobolev on this HS dot Rn, we have the Sobolev inequality holds. So now I'm in a position so that I can define what is the weak solution of the equation E, which I just wrote, scalar field equation. What do I mean by the weak solution of that equation? So we say that U in HS dot Rn is a weak solution if this variational formulation holds. So you see U phi inner product in HS dot Rn plus integration Vx U phi equal to integral Gx U phi dx. This should hold for every phi in HS dot Rn, and if all this integration makes sense. So why did I write all this integration makes sense? Because it depends, I mean, what condition I need to put it. It need not be enough just in HS dot Rn. I may need to take more assumption, I mean, more restriction on this. It depends on the nonlinearity G and the potential function V. So for example, suppose I take V is identically 1 and G is this nonlinearity. This is the polynomial one with subcritical nonlinearity. Then I need to take this solution space as HSRN. So this plus L2, right? No, so then the left hand side becomes the HS inner product, and right hand side should be finite by using Helder inequality and Sobolev inequality. So then my space will be, solution space will be HSRN, not HS dot Rn. So that's what I'm saying, that it depends on this V and G. Okay. So in physical context, the question is that my equation, this E, the general scalar field equation, where does it appear, or what is the, I mean, from where it comes, the equation. So this kind of equation, it appears in the fractional cases, in the non-local case, in the study of standing wave for fractional Schrodinger equation and fractional Klein-Gordon equation. In context of fractional quantum mechanics, nonlinear fractional Schrodinger equation was proposed by Lasker in 2000-2002, two consecutive paper in modeling some quantum mechanical phenomenon. In particular, it arises in evaluating Feynman path integral from Brownian-like to the Levy-like quantum mechanical paths. For more precisely, suppose you consider this is the Schrodinger equation. Okay, psi is a complex function, complex valued function defined on Rn times R. So now if you have this nonlinear, suppose use this Gx psi, this has this nonlinearity has this form, so it's homogeneous in this variable and it's continuous, it's assumed at this Gx0 equal to 0, then one can actually look for standing wave solution, that psi x equal to I omega t ux, omega is this one. If you just substitute that, then it leads, actually this leads us to the finding out the solution of E. We go back to the scalar field equation. So it's enough, I mean, not enough, I should say, it's very important is that you understand this equation, E scalar field equation. Okay. Now I go back to the standard classical case S equal to 1. In S equal to 1, where this kind of equation appears in many physical contexts, for example, like statistical mechanics, false vacuum in cosmology, nonlinear optics, laser propagation, etc. And they are also called the nonlinear Euclidean scalar field equation. Mathematically, analytically, it was studied by many mathematicians, started by Beristes-Lyons in 1983, and afterwards there were many studies, like some of the famous paper in this area by Digny 1986, Barili 90, Delpino Feldman 96, Wang 93, and most of them dealt with the existence and multiplicity of solution under various assumptions on the potential function V and the nonlinearity G. In the non-local case, so in S is in 0, 1, multiplicity, existence and multiplicity have been obtained for E using various variational technique. For example, some of the quite famous paper I'm just mentioning. There are many works in this direction. So like Fellmer-Quast-Tang in 2012, they have considered the equation E when V is identically equal to 1, and nonlinearity is the nonlinearity is the superlinear nonlinearity, and it's a subcritical superlinear nonlinearity and satisfying Ambrosetti-Rabinowitz condition. Okay, so they proved that existence of solution, and they studied the symmetry of positive solution, whether the solution is symmetric or not. They have shown the symmetry. Now in Sechin 2013, he has considered the equation where the potential V satisfies certain asymptotic assumption as mod x goes to infinity, and the nonlinearity is again superlinear subcritical, and he has obtained existence of ground state solution. Then Frank Lenzman Silvestre in 2016 in a celebrated paper, they have considered E with V identically 1. Again, G is the subcritical nonlinearity, and prove the uniqueness and non-degeneracy of positive ground state solution. So there was one paper which I forgot to mention, and in this direction, where Frank Lenzman first in I think 2014 Acta Mathematica studied the same equation in dimension 1 and proved the uniqueness and non-degeneracy. And later they, in this paper, they have generalized this in the higher dimension case, uniqueness and non-degeneracy of positive solution. But uniqueness is, the full uniqueness is still an open problem. So also I forgot to mention that Frank Lenzman Silvestre also have shown that any positive solution is radially symmetric, and it has this asymptotic behavior, that it at infinity it decays of this rate. It's the exact asymptotic behavior. Okay, as I was saying, that uniqueness for, so what they have established is that uniqueness of ground state solution, which is a remarkable paper and remarkable, it's a very, very celebrated technique that they got, but that is still for ground state solution. Uniqueness for this solution, the subcritical case, fractional Laplacian, it is still open. In the local case, S equal to 1, this uniqueness was proved by Nong 1989 using ODE techniques, which does not work here. And in the non-local case, which is what uniqueness is known for this one, is one-dimensional case, n equal to 1, s equal to half, and p equal to 2, square nonlinearity. So Amick and Tolan in Acta Mathematica 1991, so they have proved this uniqueness for one-dimensional case equal to 2. Again, it was used heavily that it is a square nonlinearity, and they used complex analysis since it's an R1, so they used complex analysis techniques, which again does not work in the higher dimensional case and general nonlinearity. So now I just, next I considered V is equivalent to epsilon. So like Vx is a small epsilon x, V is epsilon, and Gxu is this nonlinearity, okay, where Q is strictly greater than P is strictly greater than 2. So here we can include all kind of P, like it is, P could be subcritical, P could be critical, P could be supercritical, okay. And I consider this equation. So I consider this equation. So this is my P epsilon, and I will next few minutes I will just deal with this epsilon, this equation P epsilon. Okay. In the local case, S equal to 1, existence of positive ground state solution for sufficiently small epsilon was proved by first by Strauss, but they were proved in he able to prove it in certain range of this, not full range, and finally Berestitsky-Lyons in 1983 proved the existence of positive solution for small epsilon in the full range. Uniqueness, okay, after small epsilon it does not exist, positive solution does not exist, and one can actually prove that using Pozai. So uniqueness of positive solution was proved by Serintang when S equal to 1. Again, I'm talking about in the local case using ODE technique. Complete characterization of asymptotic profile of ground state solution of this as epsilon goes to 0 was studied by Moroz-Muratov in 2014. So now I just will mention some of my result in this direction. for the non-local case, when S is in 0, 1, for this equation P epsilon. Okay, so it was a joint work with my former PhD student. So it's 2019, last year, sir. So we proved that any solution, if we take any positive solution of that equation P epsilon, that is actually a classical solution. And any positive solution has this a priori estimate that it is strictly, any positive solution is strictly less than 1. It goes to 0 at mod x goes to infinity. And not only that, we have established exact asymptotic behavior as mod x goes to infinity. And then we have proved that the existence of solution that there exists a small epsilon, there is a small value epsilon star, such that if epsilon is smaller than that, then it admits a ground state solution. So what is ground state solution? That is the minimum energy solution. Okay, and it's radially symmetric and symmetric decreasing. Then we have proved using moving plane method that any positive solution, if you consider, any positive solution, if you consider for this P epsilon, so you take any positive solution for this, we have shown that any positive solution have to be radially symmetric and symmetric decreasing. So next we're interested that what happens to the asymptotic behavior of U epsilon, the ground state solution. As epsilon goes to 0, how U epsilon behaves. And it actually changes, it varies whether we are studying the case P is subcritical or critical or supercritical. So P equal to 2 star is called the critical case. So in the critical case, what we have proved that up to a rescaling, there exists a rescaling, that if you consider this rescaling, U epsilon is a ground state solution. Okay, so we know that it's a radially symmetric and decreasing. So what you can do is that without loss of generality, you can assume that the maximum of U epsilon, for each epsilon, maximum of U epsilon is at 0, because if not, you just translate it, because it is translation invariant, and you know that it is radially symmetric and decreasing. So you can assume that the maximum is at 0. Now you consider those sequence of U epsilon as epsilon goes to 0, and you consider this rescaling. And what we have proved that up to this rescaling, this one V epsilon tilde actually converges to the solution of this Yamabe equation, fractional Yamabe equation, in this Helder norm HS dot norm. And we have the exact asymptotic behavior, as I said. So we have this exact expression that lambda epsilon tilde this behaves like this, and U epsilon 0 behaves like this. Okay. And when it was for the subcritical case. Now when it was for the critical case. And now if P is subcritical, that P is strictly less than 2 star. So here you notice that here it is anything, there is no restriction on Q. Q could be anything. Could be critical, supercritical, subcritical, anything. Q is just greater than P. We have the restriction only on P. Okay. So now when P is subcritical, then again there is a scaling. Up to this scaling, we have proved that this converges to the unique ground state solution of these equations. This I mentioned that Frank Lenzman Silvestre have proved uniqueness of ground state solution for this equation. So we have shown that U epsilon up to a rescaling in the subcritical case converges to the solution of this one, unique ground state solution of this one. And this is the exact asymptotic behavior. So as one can see that as we have assumed that maximum is at 0. So from this subcritical case and the critical case, so in the subcritical case, you see this, we have this U epsilon 0 is epsilon times what this sum. This is a positive exponent, right? So as epsilon goes to 0, this goes to 0 in the subcritical, and similarly in the similarly in the critical case. In the critical case also it goes to 0 as epsilon goes to 0. So so when you see that U epsilon goes to 0 as epsilon goes to 0 in the subcritical and critical case, and it is consistent with the observation that if you consider P naught, that is epsilon equal to 0, the equation with epsilon equal to 0, that does not admit any finite energy non-trivial solution when in this P is subcritical or critical and Q greater than P. So that means what happens that when we have a solution in the subcritical and critical case, but as epsilon goes to 0, it vanishes actually. And we have the exact asymptotic rate at which rate it vanishes, goes to 0. Okay. Now, next case is that supercritical case, that P is supercritical. So in this case, if we have proved that U epsilon actually converges to a ground state solution of this equation. Okay. In Helder norm, HS dot norm, here we do not have exact asymptotic behavior because here the uniqueness of this problem is not known. In other two cases, we have the uniqueness was known for the limiting problem. Here it is not yet known because it is yet open problem. So existence of ground state solution for this equation was proved with my former student, that's Devangana Mukherjee in 2017, but uniqueness is still open. And in the local case, A is equal to 1, uniqueness for this was proved by Nong, MacLeod, Pelletier, and Troy 1992 using ODE. Again, which does not work here in this case, in the fractional Laplacian. So as I mentioned, for this equation, P epsilon, let's go back to P epsilon. Yeah, this so here we have the in the local case A is equal to 1. One has the uniqueness of solution, as I mentioned, it was proved by Sarintang. But in the non-local case, uniqueness is not known. Okay, so what based one can try to do is that at least can we establish some asymptotic uniqueness? What do I mean by that? Suppose you have two ground state solution, U epsilon and V epsilon, which has the same asymptotic behavior, that as epsilon goes to 0, it behaves same. So question is then can we say that they are actually same for a small value of epsilon? The answer, we prove that yes. So that's the local uniqueness we prove for the critical and subcritical case. So we prove that suppose you take two ground state solution which have the same asymptotic behaviors, that is that with this same rescaling, it goes to that Yama solution of Yama equation. Then we prove that this U epsilon 1 and U epsilon 2 has to be same when epsilon is in this interval. There is a small epsilon naught for which below that they have to be same. And same thing we prove it for the subcritical case as well. But we do not, we not have this result. I mean, we could not prove this result for the supercritical case, P strictly greater than 2 star, because we do not have uniqueness for this yet known. And I need to, to prove this result, we need to have uniqueness for the limiting problem, uniqueness of ground state solution for the limiting problem. Okay, so I go back to this equation go back to this equation E, when I consider V, the potential function V is 1 and the nonlinearity again subcritical nonlinearity. So I just said that we know the uniqueness of ground state solution for this one from Franklin and Sylvester for ground state solution. Now I give a little bit perturbation to this equation. So just to put a perturbation here by a function, the coefficient function AX, and put a non-homogeneous term here, okay, fx. So why I'm calling a little perturbation, because I'm taking a L infinity function, positive L infinity function, and which goes to 1 asymptotically. And f is a function in the dual space of HS. So it's the dual space non-negative functional. Okay, then what do I mean by non-negative functional? That if f acts on any non-negative function u in this, then this dual space action, so that is greater than equal to 0. So question is that, so if we give us this perturbation, does the small positive solution still survive? So that's what we want to study, okay? So here we have divided the study in a couple of cases. One condition, we study that when A is greater than equal to 1, then we study when A is less than equal to 1, then we take A equal to 0. Some few cases we try to break up this problem. So in a joint work with Devdeep Ganguly and my student Shoptik Chakraborty, first we have proved that when A is greater than equal to 1, we have this asymptotic behavior that A goes to 1 asymptotically, and it's always positive and L infinity. This assumption we always have, okay? With this assumption, additionally, suppose we assume that A is greater than equal to 1, then we should prove that then we prove that this equation admits two positive solution. We get multiplicity, at least two positive solution when this dual space norm of this one is sufficiently small, and we give exactly how much small it is. So you see that if this dual space norm is less than this, then that admits at least 2 positive solutions. Okay, and when what happens when a less than equal to 1? So when a less than equal to 1, I need an additional assumption. We need an additional assumption on that we know that a asymptotically goes to 1, but we need additionally that in which rate it goes to 1, or the control on the rate. So suppose we assume that this asymptotic, suppose you assume this control on this rate. Then we prove that, and also infimum is strictly positive. Under that, we prove that when this dual space norm is sufficiently small, then this equation Q, it admits at least 3 positive solutions. Next, we studied what happens when f is identically equal to 0. Just a second, yeah. Okay, so there is something is still left. It could be that a need not be greater than equal to 1, or a need not be less than equal to. It could be in between also, right? It can oscillate also. Since that is still open. And now I'm considering, suppose this equation with f identically equal to 0. So you have just only this portion. Okay. Which one? Yes. So we have now A is, now here we have just A is L positive and L infinity. I do not have any assumption on greater than or less than. Is L infinity and positive function, and infimum is some A naught, which is strictly positive, and asymptotically also it goes to A naught. Under that assumption, we have proved that this problem admits at least one positive solution, admits a positive solution. Next, we go to this, I think I have 10 minutes left. Okay. So next we go to the system of equation, this scalar field equation with the, so far we were discussing about the scalar equation, single equation. Now if you go to the system of equation, weakly coupled system of equation, scalar field equation. You see here, this is the scalar field system of equation, weakly coupled, because you see here U and V both are involved. And I have the assumption that here alpha plus beta strictly less than 2 stars. So it's the subcritical case. Okay. So we are interested in studying the, again, existence and multiplicity for this equation. F and G are again dual space function. So F and G belong to the dual space of Hs. So that belongs to H minus S Rn. Okay, and so what should be the solution space? The solution space is the Hilbert space, natural solution space, the Hilbert space HSRn times HSRn. So this is the Cartesian product of HSRn times HSRn, and we have the inner product, which is the, you take that pairwise inner product. So the inner product is defined in this way. You take inner product of U and phi and plus inner product of V and psi. And you have the corresponding norm in HSRn times HSRn. Okay. And what do we mean by the solution, weak solution? So this is, so UV in HSRn times HSRn is said to be a solution. Just a second, please. So we said that a couple UV in HSRn times HSRn is a solution for this system of equation if U and V are positive, because we are positive, we have here, that is why. And it satisfies this variational formulation for every phi psi couple in HSRn times HSRn. So this is the inner product between this, and this is the one. Okay. And the question is that where this system of equation arise. For example, like scalar field equation, it's a scalar field system of equation, or Schrodinger system of equation, this kind of system of equation, where it arises, or what is the application. For that, there are some application in biological and applications and physical application. For example, like in population dynamics and nuclear reactor, and in terms, here I mentioned some of the mathematical study of elliptic system, or Schrodinger, in particular Schrodinger system, because we are interested in the scalar field system of equation, Schrodinger system. So for S equal to 1 in the local case, I mentioned this some of the paper like Mitederi 1996, Alves Moraes Suoto in 2000, Lin Wei 2005, Witness Suple 2004, Rachel Zhu 2000. Some of those were for S equal to 1. Now, if you go to S is in 0, 1 in the non-local case system of equations. So there are not many papers and where this kind of system of equation in the interspace Rn were studied. So most of the paper where where the system of equation for this Schrodinger scalar field system of equations were studied were for the Dirichlet problem in the bounded domain for the Dirichlet boundary condition that outside it is the bounded domain. So some of them I can, some of them I just mention here. So one is my joint work with my collaborator Fuktai Wayne, which appeared in this year. So there we studied system of equation, Lane-Emden system of equation in the fractional case, fractional Lane-Emden system of equation, but in the bounded domain, as I said, with Dirichlet boundary condition. But we in measured data. So it's a Lane-Emden system of equation with measured data. Measured data is in the domain. Okay, so and we have proved existence and multiplicity of solution. We prove existence, multiplicity of two positive solution. Okay, what do I mean by positive solution for a system? I just meant that to each component, if you consider the couple UV, each component is positive. Also, there are some of the very good paper in this direction for the system of equation in the fractional case. Fractional case with the bounded domain were studied as Chen Squasina 2016, Costa Miyagaki Squasina Young 2015, Faria Miyagaki Pereira Squasina 2016, Giacomoni Duina Mukherjee Srina 2018, and so there where existence and multiplicity, such kind of problem are addressed for the bounded domain. For the non-local system of equation in the interspace Rn, we refer, there are, as I said, there are very, very few. We refer Fisela, Pucci, Saldi 2017, Fisela, Pucci, Zhang 2019 to paper. So, so I just go back to the system again. Yeah, so we are interested in existence and multiplicity for this equation. So what we have proved is that, so it's a joint work with Patricia Pucci and my PhD student Shoptik Chakraborty. So we have proved that if F and G are non-negative, non-trivial functional in the dual space, so they are non-trivial, you cannot take identical as 0. F and G are non-negative, non-trivial functional in the dual space with the kernel are same. With kernel of F is same as kernel of G, and if they are in the dual space, their norm is small, sufficiently small, then that system admits a solution U bar V bar such that each component is positive. And also then the question is that how do we know that U bar is not equal to V bar? If U bar equal to V bar, then it will reduce to an equation again, right? So it's no more longer, it will no longer be a system. So what we show that if F is not identically equal to G, or alpha is not identically equal to beta, at least one of them should be different. Either alpha is not equal to beta or F not identically equal to G. Then we show that U bar is not same as V bar. So it's actually, it's a system, true system. So we just prove the existence here. We couldn't prove the multiplicity. Multiplicity is yet an open problem, and we do not know how to, get the multiplicity of solution in the vectorial case. Also, as far as I know, the multiplicity for this problem, even in the local case is equal to 1, it's not yet known. So we are still trying. So that's all I want to say, and thank you.
Okay. Yeah. Thank you so much. Thank you. Is there any questions or comments? Okay, I have a question actually. You are considering on the right hand side that you have a special kind of nonlinearity, like mod u to the power p minus 1 into u, something like that. So my question is like, is there, I mean, what's the motivation behind that? I mean, is there any kind of physical phenomena
Do you mean
involved there? Yes, yes, yes.
yeah. Okay. So for
Yes.
P greater than, if you take the critical or subcritical using Prof, you can show that no existence of solution. So this one, if I, can you see my screen?
Right, right, right. I can see. Yes, yes.
So for the critical or subcritical, this problem does not admit any solution, and that one can show by Prof identity. So when it is subcritical, so this is this problem. I mean, and as I was saying, it's the scalar field equation, and it has, I mean, existence, and why people are interested in it, the uniqueness, existence, like as I was showing that, I mean, the unique, first of all, it has a several connection with the, I mean, scalar field equation. It comes from actually Schrodinger equation and all. So if you go back to the those kind of equation, so the limiting problem will be this one. Also, if you consider the Partab equation with this epsilon parameter, you see that you come back to this case, this equation, this kind of equation, right? So so to understand the uniqueness, it's very important to know the existence uniqueness for the stability purpose. It's really important to know. So then we can, then one can study various other problem associated with that. That's one point of.
So this particular form of nonlinearity is very important. I'm saying, yeah. I
Yes.
mean, this particular form of, for instance, in place of u on the right hand side, if you have gradient nonlinearity, for instance, gradient of modulus
Yes,
gradient of
that's
u to the power
actually
from p
very
minus to
interesting. Yes.
gradient of u, then
Mhm.
is this
Yeah,
make?
so
I mean, I don't.
so
There
there
any
are
kind of
some works. Yes, there are some works. I can say that there are some work for the gradient nonlinearity. I think it's very new and very recent work. Some going on. I think I saw a couple of papers, recent paper. But I do not remember. It is on the left hand side. It is fractional Laplacian U plus U type of term or not, or is it just fractional Laplacian type U when the gradient nonlinearity was considering? But yes, you are right that with the gradient nonlinearity need not be polynomial, but okay, to start with some gradient nonlinearity and to study that equation, mathematically it is interesting. I do not know the physical context with this left hand side is this kind of fractional Laplacian plus U that is coming from the Schrodinger or scalar field thing. From physical point of view, what, the interpretation, whether it is interesting or does it have any physical interpretation, that first one needs to check. Mathematically, I can say that with gradient nonlinearity, it will be interesting to check, but first one check that whether it has real motivation coming from physics or somewhere else. Then one, but I am not sure that. I have to check that one.
Thanks. Yeah, just one more thing, just for
Yeah.
I mean, I'm a little bit curious about that. For instance, left hand side, I'm not talking about fractional Laplacian. Let's say s equal to 1.
Mm-hmm.
And instead of Laplacian, if you just replace by another other kind of linear operator, for example, conductivity equation like divergence A, like divergence sigma gradient. Sigma is the conductivity of the medium. Do you think all the I mean, everything will work for that equation? For instance,
Not at all.
exactly the same equation,
Not
like
at all.
in place of Laplacian, you are just replacing a minus Laplacian by some linear operator with some coefficient involved inside. For
Yes,
example, divergence sigma gradient.
suppose you are thinking about, say, P Laplacian first non-degenerate or just this kind of.
P Laplace is still, it is difficult for the moment. Let's
Okay,
say Laplacian, I am just considering any linear elliptic operator in place of Laplace. I am just replacing Laplace by linear elliptic operator. And that operator involves some coefficients and all these things. Do you think everything should work like existence? And certainly that will depend on the coefficients and the regularity of that coefficients and so on. Yeah.
well, exist extent may follow, but then the question is uniqueness. Uniqueness, also you are talking about this in the local case, right? S equal to 1.
Yeah, for instance, S equal to 1.
Yeah, because the if you go to the non-local case, S equal to 1, as I was saying, uniqueness is a very big problem, and this that is why the CPM paper of Frank Lenzman Silvestre is the kind of Bible so far in this direction, which came in 2016, which is a remarkable work, and that's the only available kind of sort of technique in this direction. So, I mean, uniqueness, non-local, I do not know at all. I do not know, but the local case, uniqueness again will be a challenging one. There one can try with ODE thing, but it will work or not, I cannot just comment. One has to really work hard to see. About the existence, I think it can be shown, but the uniqueness and other analysis, it's nothing I can just straight away comment that it will work. One has to really see that it will work or not. But it will be nice to see if...
Okay.
Yeah. Hello, this is Sudhakar Chaudhary.
Yes.
I have one just doubt. I don't know how much it is meaningful. The PD which we are considering is in Rn. So what about if we consider these type of PD in bounded domain? I mean,
well, this is, as I said, that the topic is scalar field equation. So scalar field equation and coming from physics point of view, right? And Schrodinger equation, scalar field equation, it's coming from there. So that is why it is the entire Rn, this equation. Okay, and if that is why it is always Rn, because this equation coming is entire space Rn. Now, if you just want to, just mathematically speaking, if you just want to know that suppose this equation, I mean, there exists a solution or not in the bounded domain, you can immediately, what you can try to do is that check with the Pohozaev identity. In the bounded domain, you do have a solution. I think that you it does not admit a solution in bounded domain. With the you can just try with Pohozaev type of argument, Pohozaev identity. So, and Rn here is why it is it's coming from physical context, as I was saying. Okay.
Okay. Thank you.
Hello, Mousomi, this is Indranil.
Yes, Indranil, say. Please.
Yeah, I mean, I have probably a stupid question, but okay,
No question is stupid. Come on, tell. Yeah.
Yeah, I mean, so far, what you are talking about this V, the potential is only constant. So, is it like what is the current research? I mean, it is only for the constant potential.
No. There are coefficient with the coefficient function generally. I mean, with coefficient function and certain assumption on coefficient, there are also some studies there. You can find the literature. I mean, if you want, I can send also some literature. So here,
sorry, I cannot hear you properly. Can you repeat once more?
Yeah, so there are some results on with the potential function V. So I think I can send you some of the papers with the potential function V. Okay, and some of the existence and other studies. So here I wanted to first put a simple case that to understand, since it was the expository type of talks, I wanted to keep it simple. So I just keep that everything constant type of, but there are some works where existence have been studied, existence, multiplicity, such kind of things have been studied with the potential function.
Okay, and yeah, and one more thing. So I was looking at the norm which is like HS dot intersection with the C2S minus sigma.
Just 1 second, let me just go to this slide. This one you are talking?
No, before that, the multiplicity result.
Which multiplicity result?
Where you have a difference of two u to the power p minus 1 u minus u to the power q minus 1 q. Yeah, this one. Yeah, sorry.
This should be this. I mean, we show the convergence in not only just HS space but also in space.
Yeah, and this is okay. So this norm is equipped with the HS norm, or it is equipped with the C2S minus sigma?
No, it is equipped only with HS norm.
HS norm. Okay. Okay, then.
But
Okay,
if you have the more, if you have the convergence in the Helder norm also, that's much better, no?
Yeah,
So,
right. I mean that. Okay, yeah, yeah. Okay. It's only on the HS norm. Okay. Okay.
HS norm, only HS norm. The way we define the variational solutions, only in HS. But solution is also class. Here we showed that the any positive solution is actually a classical solution.
Yeah, but with C2S minus sigma, you cannot get a classical solution. Yeah. Okay. All right. Thank you very much. It's a nice talk.
Thank you.
Hello, ma'am. I am Nivedita. I have a question. Ma'am, there we take a restriction on P, that is 1 less than P less than N plus 2S divided by N minus something. Why we need?
Just a second.
In the letter.
Letter?
Yes, ma'am. Yes, here. And the restriction of P, that is less than N plus 2S and N minus 2S. Why we need that?
This is the subcritical case I'm talking about, because if you take P bigger than that, the solution does not exist. You can try to show that using Poiseuille kind of argument, that Poiseuille type of identity. So try to suppose you assume that it has a positive solution and try to get a contradiction using Poiseuille type of argument, which is called Poiseuille identity or non-existence result. So you can try to show that that does not admit any positive solution. If solution exists, it will be identically 0.
Okay, that is trivial solution.
Yeah.
Thank you, ma'am.
Yeah, any more questions? Yeah, if not, then we can thank the speaker. Yeah, thank you so much. Thank you, Mousomi. Yeah.
Thank you very much also.